Tajikistan is one of the poorest countries in Central Asia, landlocked, with limited fossil fuel resources, a population of just over 10 million people. Yet in a remote valley along the Vakhsh River, this small nation is pursuing an ambition far beyond its own scale, building the tallest dam in human history. With an estimated total cost of around $8 billion, the Rogun Dam is designed to stand 335 meters tall, surpassing every existing dam and any skyscraper currently standing in the world. The project is planned to generate 3,600 megawatts of electricity, equivalent to the combined capacity of multiple nuclear power units. But to understand why a country like Tajikistan is willing to stake nearly its entire future on a single dam, join Mandarin Tech as we turn back time, far back into the past. The idea of the Rogun Dam is not a product of the 21st century. It first emerged in the 1960s, when Tajikistan was still a republic of the Soviet Union. In the context of the Cold War, Moscow was pursuing an ambitious strategy, industrializing its peripheral regions, especially Central Asia, through massive infrastructure projects. The Vakhsh River, a major tributary of the Amu Darya system, quickly came into focus. With its powerful flow, high mountain terrain, and dramatic elevation drop, this was one of the few locations in the world capable of supporting the construction of ultra-high dams. In 1976, the Soviet Union officially launched the Rogun project. The objective was clear: to build a dam that would surpass all previous hydropower projects, one capable of controlling the river, generating electricity on a massive scale, and regulating water for the entire region. But history did not follow the plan. After the collapse of the Soviet Union in 1991, Tajikistan descended into civil war. Its economy collapsed, and Rogun, still only a partially built construction site, was abandoned. It would take more than 2 decades for Rogun to have a chance at revival. According to engineers, when completed, the Rogun Dam will stand 1,099 feet tall, equivalent to approximately 340 meters. This will make it the tallest dam ever built. The Rogun hydropower plant is designed with 6 turbine units, with a total installed capacity of 3,600 megawatts. This amount is sufficient to double Tajikistan's current electricity output, creating a significant surplus of power during the summer months. Rogun is not a conventional concrete dam. It is a rock-filled dam with a central clay core. The dam body is formed from hundreds of millions of tons of rock and gravel, compacted layer by layer. The clay core serves as an impermeable barrier, while the massive rock-filled shoulders provide structural stability and energy absorption. The reservoir behind the dam has a capacity of approximately 13 cubic kilometers of water, making Rogun one of the largest reservoirs in the region. This volume allows for seasonal flow, regulation, more stable power generation, and support for irrigation in downstream areas. Everything begins with diverting the river, because in order to build the dam, the foundation area must be kept dry. For Rogun, this meant drilling massive diversion tunnels through the mountainside. 4 tunnels were designed, each more than 1 kilometer long, with diameters reaching tens of meters. 2 of these tunnels were constructed during the Soviet era and were later rehabilitated and reinforced. The remaining 2 were completed during the project's restart phase. These tunnels allow the Vakhsh River to bypass the construction site, clearing the way for the main construction phase. Before the dam body could begin to take shape, the foundation of Rogun had to be treated thoroughly. Weathered soil, rock, and weak materials at the valley floor were excavated to expose stable bedrock. Natural fractures within the rock mass were drilled and injected with high-pressure grout to reduce seepage, strengthen cohesion, and control groundwater flow. At the same time, a foundation drainage system was installed to reduce uplift pressure beneath the dam throughout the structure's entire service life. In parallel with foundation treatment, the rock slopes are reinforced through rock bolting, steel mesh installation, shotcrete spraying, and drainage to ensure long-term stability before dam embankment begins. Once the foundation and slopes meet safety requirements, The Rogun Dam body is constructed in stages under a strictly controlled process. Rock and gravel are extracted on site or transported from nearby areas, then placed in thin layers, leveled, and compacted to ensure long-term stability and minimize uneven settlement. At the center of the dam body, the clay core is built simultaneously and carefully protected to maintain impermeability. Throughout this process, engineers continuously monitor settlement, water pressure, and dam deformation, while inspecting and test operating the discharge and control systems to ensure all parameters remain within safe limits. At the same time as foundation works are completed, the spillway structures and vertical shafts are constructed deep within the rock mass through vertical excavation, reinforcement installation, and staged concrete placement, forming safe water conveyance paths and controlling hydraulic pressure throughout both the construction and operational phases of the dam. After the vertical shafts and tunnels are fully excavated, the tunnel structures are constructed by installing reinforcement, formwork, and placing tunnel lining concrete in segmented sections, forming a load-bearing and waterproof lining for the tunnel system and discharge routes. Next, the tunnel invert and the floor of the discharge structures are completed to provide a stable load-bearing foundation for the entire system. Reinforcement and drainage layers are installed before the floor. Concrete is poured in segmented sections, ensuring strict control over thickness, strength, and surface quality. The first two turbine units began generating electricity in 2018 and 2019, marking the transition from a purely construction site to an operating power plant. The electricity produced during this phase both supplies domestic demand and allows engineers to verify the design and operating systems under real conditions. According to the current plan, the dam body is expected to reach its design height around the year 2029. However, reservoir impoundment will be carried out cautiously and over a longer period. It is projected that the Rogun Reservoir will reach its maximum water level around the year 2036, fully completing the dam's role in regulation and power generation. For Tajikistan, the Rogun Dam is not merely an engineering project, but a national-scale financial gamble. The total construction cost is estimated at around $6.3 billion, an amount equivalent to nearly half of the country's GDP. For a small economy with limited revenue and heavy reliance on remittances, this represents an unprecedented financial strain. For many years, Rogun suffered from severe funding shortages. International donors remain cautious, not only because of the dam's immense scale and technical complexity, but also due to the political risks surrounding the project. The core of these concerns lay with downstream countries, particularly Uzbekistan, whose agricultural sector depends heavily on water from the Amu Darya river system. The prospect of Tajikistan controlling a massive upstream reservoir raised long-term water security fears across the region. In this context, the World Bank agreed to become involved only after demanding a series of independent feasibility studies and comprehensive regional impact assessments. If Rogun is a survival gamble for a small, resource-poor nation in Central Asia, then the Three Gorges Dam stands as a demonstration of how a single dam can reshape the economy and energy order of a superpower. With its massive scale, the Three Gorges Dam has become the backbone of an entire hydropower ecosystem along the Yangtze Valley. Standing taller than a 60-story building, it creates a reservoir so large that it has reshaped the entire landscape of the Three Gorges region. At full operation, this mega dam can cut up to 100 million tons of carbon emissions each year and regulate the river flow for a region home to more than 400 million people, an impact far beyond what raw numbers can convey. Its greatest influence, and also its quietest, is flood control. Before the dam existed, the Yangtze Basin suffered multiple historic floods. In 1931, floods killed more than 145,000 people directly. In 1954, the death toll surpassed 30,000. And by 1998, raging waters swept away thousands of villages, took over 3,000 lives, and caused China tens of billions of dollars in losses. These numbers explain why China felt compelled to build a water shield strong enough to tame one of Asia's most unpredictable and destructive rivers. The construction journey of the Three Gorges Dam truly began in 1994, when engineers started preparing a foundation strong enough to support a concrete structure 2,245 meters long, 181 meters tall, and nearly 115 meters thick at its base. A mass that must withstand the pressure of billions of tons of water pushing against it every day. To achieve this, tens of thousands of workers had to remove an enormous volume of earth and rock, carving out deep foundation pits that reached down to bedrock layers of granite hundreds of millions of years old. Each foundation pit functioned like a geological cross-section, exposing the backbone of the Three Gorges Valley, where only solid, unfractured bedrock could support a megadam of this scale. Here, a massive network of grout holes stretching thousands of meters was drilled and injected with cement slurry, bonding the entire rock foundation into a single, unified block and sealing even the tiniest cracks so that water could not seep through. Every section of the foundation was monitored with geotechnical sensors to ensure no weak points existed. It is this mountain-solid foundation that became the footing for the entire megastructure, allowing the Three Gorges Dam to stand firm against the powerful, surging force of the Yangtze River for decades. Once the bedrock had been transformed into a stable foundation, the concrete pouring phase of the Three Gorges Dam unfolded like a river of materials flowing through the construction site. Overhead, the steel arms of 20 tower cranes constantly swung back and forth, lifting and lowering batch after batch of concrete into more than 230 pouring blocks, stretching along the former riverbed. On the ground, mixer trucks and pumping systems worked in perfect rhythm, delivering the heavy gray mixture to its precise locations as if the entire site were breathing to a single heartbeat. Every layer of concrete had to meet strict standards for thickness, moisture, and curing speed, because even the slightest deviation could create weak points in the entire structure. Inside each block, a cooling pipe system reached deep into the core to keep temperatures stable and prevent expansion-related cracking. Surrounding it, geotechnical sensors captured even the smallest movements. Subtle signals invisible to the eye, but critical to the safety of the dam. Day after day, new layers of concrete were poured over the previous ones, tier by tier, until the total volume placed surpassed 28 million cubic meters, forming an enormous, rock-solid mass ready for the next stages of the Three Gorges megaproject. Before the project could move on to construction at higher elevations, engineers had to solve the most critical challenge: how to relocate the entire Yangtze River into a temporary passage while still handling its massive flow. To do this, a system of diversion tunnels was built as a strategic phase of the project, consisting of 3 tunnels carved deep into the mountainside. Each tunnel stretched more than 900 meters in length and stood 18 meters high, large enough to let the river pass through at speeds of up to 11,000 cubic meters per second. During construction, over 1.2 million cubic meters of earth and rock were removed using drilling and mechanical cutting to avoid any vibrations that could affect the bedrock foundation. Once the river was fully diverted into these tunnels, the original riverbed instantly became a dry work surface, protected by cofferdams and high-capacity pumping stations that kept conditions stable regardless of rain or flood season. As if a massive architectural form were slowly taking shape in the valley, the body of the Three Gorges Dam began to rise layer by layer with each new lift of concrete. Across a construction site spanning more than 100,000 square meters, steel scaffolding, hydraulic lifting platforms, and mobile gantry cranes formed a dense web of equipment, allowing thousands of workers to operate at multiple elevations at the same time. This enormous structure was reinforced with more than 400,000 tons of steel tied together across 28 dam segments running along the mountainside, creating a solid metal skeleton before each new layer of concrete was added. Each segment of the dam body was raised by 1 to 2 meters per cycle, forming giant steps pressed against the cliffs on both sides. Expansion joints were strategically placed to disperse stress, while shear-resistant steel plates tightened each connection to ensure the entire dam operated as a unified structure. As it rose, the structure gradually tapered toward the crest, where the top width narrowed to just 40 meters, reaching the designed height of 185 meters. The critical milestone needed to create a reservoir holding nearly 39 billion cubic meters of water behind it. Rogun Dam is not just a hydropower project. It is a stress test for everything Tajikistan has placed its bets on: engineering, finance, politics, and its future in a world of rapidly accelerating climate change. If successful, Rogun could transform a poor nation into an energy hub of Central Asia. If it fails, it will stand as one of the most expensive gambles in modern infrastructure history. But the final question is not simply how tall Rogun is or how powerful it can be. The real question is whether a single dam can carry the future of an entire nation on its shoulders. When upstream glaciers are retreating, downstream pressures over irrigation and economic interests are mounting. And in between lies the challenge of capital, timelines, and trust. If you want to follow the world's greatest infrastructure stories, where engineering collides with geopolitics and the future is shaped by concrete, rock, and water, subscribe to Mandarin Tech and leave a like. See you in the next video.